Hello, my name is Hyuk Lee and I'll be presenting my Lab 3, Magnetic Field of Bar Magnet Lab Report. So first for some introduction and background. So the whole purpose of this lab was to further explore the Biot-Savart law. In addition, we also wanted to measure how exactly distance affects the magnetic field caused by a small bar magnet. So there were a few fundamental principles that went along with this lab. So first we have a variation of the Biot-Savart law. So on the left you can see the B bar is equal to K R to the power of N. So this N here is what we find through our data. However, we expect N should be around like -3 because we expect as the distance to increase, the magnetic field to decrease. So on the right we have the magnetic field due to dipole. So this is another one of the equations that we are given in this lab and we have to use. In addition, we have the law of superposition, which basically says the magnetic field net is equal to all the individual magnetic fields added up. So for the experiment, so on the left you can see the image of exactly how we set up and how we find where the magnetometer is in our phones. We have to find both the X and the Y, and then we can locate it on our phone using tape. And then the right image is, so basically what we do is we find different distances on the ruler, and then we use the same X and Y distances, and then we find the D distance from that. And we have to record each of the BY, BX, and BZ. So for the on-field magnetic field data we have here, so this is when we put the magnetometer a certain distance away from the ruler and the magnet. So each of these are the distances for 20, 140, 260, 380, and 500 microteslas. So with that data, we created a graph, and then we have this equation right here, y equals -2.4417x minus 13.837. So here we found our n to be -2.44, so that's a bit less than the -3 that we expected. However, since we're taking data ourselves, there's bound to be some error, so this is reasonable. And then from k, so we know that k is equal to e to the power of this constant that we got. So that turned out to be 9.787 e to the -7. Then we can use that to calculate our dipole moment, mu. So then we have k over 2 mu naught pi. And then we got magnitude of mu to be 4.8936. For the off-field magnetic field, I mentioned earlier it was in the right image. So for this, we put the magnetometer a certain distance x and y away. And then we find each bx, by, and bz, and then we find the net b net. So for the code, so here we're just defining our constants. This 4.8936 is what we calculated earlier. This function right here it returns the magnetic field, so it takes mu and r, which r is the vector. So we find the magnitude of r and divide r by the magnitude to find r hat, then we can calculate b. So this part, it creates a bunch of different vectors here. And then on to the right, we create the on-axis and the perpendicular vectors and arrows for that. And then we print them out in the result, the output. And then for this, this is the average distance in the off field that we found. So we take this, we create a vector, and we find the magnetic field of that, and then we also create an arrow for that in magneta, the purple color. So here's the final glow script model that is shown. This white thing in the middle is the magnet. So from this model, we found the B to be 5.0477 e to the -5, 1.514 e to the -4, and 0. And then this turned out to be very similar to the calculated B from our experiment, or the B from our experiment. So they're pretty close, so I think we did pretty well in this lab. For some reflection questions, number 1, if you hadn't oriented your experiment to compensate for the magnetic north, then how would my results have changed? Then the magnetic field of the Earth would have affected the results. So then the values that I found, the K, the mu, they all would have been slightly different. And for question 2, if we were to stick two magnets together, how would I expect our measurements to be different? Well, I would expect the direction to be the same, but the magnitude to increase. So thank you for listening to my lab report.